Okay, so it has to be doing the classes in this mode from the time for the time being, where I will be posting a video mostly. Sometimes it can be lecture notes also, where I discuss a particular topic to be posted in the Google Classroom. I will not be, unfortunately, taking the questions while the classes are going on because it's an already made video. But you should post all your questions in the classroom comment and then you should take it up. What we'll do in the two lectures now, we'll finish off the galactic dynamics and structure part. And here I will give you a mathematical summary on the galactic structures. Vidya has already told you in detail about it, but I will just pick up a few topics and you will see that how things are actually done in practice, though I will not go into the detail because the detail is very, very complicated. The two books that one can follow for this, one is the kind of Bible for the galactic dynamics, is by Binney and Treman. It's a very complicated book. The topic itself is very complicated. So only if you have enough tenacity should look at this. The other book is rather simple version. One chapter discusses galactic dynamics. It's also not very simple, and I only will take a very few part of it. Is the third volume of the Theoretical Astrophysics series by Tanu Padmanabhan. Okay, so let us start. So let's start by asking what we have already seen, what Vidya has already taught you about galaxies. So you have learned that the galaxies comes in different flavors. One of them is called disk galaxies, where if I see from a side, the entire galaxy, all the stars lies in a very thin disk. So there is no star here or there is no star here. At the center, most of the times, there is a more spheroidal or ellipsoidal bulge. If I see the galaxy from the top, so I see kind of the entire face of the galaxy. It's often called the face on view. I see at the center, sometimes there is a bar type of structure, a little elongated linear structure. Not all the time, sometimes. I see the bulge where a lot of stars are there. And then you often see the spiral arms where the stellar density is a little more. If I have an ellipsoidal galaxy or elliptical galaxy, then the entire galaxy, which usually is a lot bigger than the disk galaxies, looks like an ellipsoid, just like the bulge of a disk galaxy. Well, we have learned about many other things. We have learned about epicyclic approximations to the stellar orbits, which we'll come back to at the end of this lecture again. We have learned about rotation curves. We have learned about virial theorems. So when you have a disk galaxy, all the stars here are being pulled at the towards the center, but the centrifugal force of the rotation mostly balances that gravitational pull. When you look at the bulge of a disk galaxy or the elliptical galaxies, it's mostly the random motion of the stars which balances the gravitational pull. So that it comes from the virial theorem that you have already learned. Vidya also has outlined at least a little bit at the last lecture about the theory behind the spiral structure. So let us ask the question that how does it all work? So what is the mathematical procedure that one follows to address the problem of structure and dynamics of a galaxy in general? So that's the first question that you're going to ask in half of the lecture today. Well, the basic mathematical framework is already known to us. It was taught to you by Vidya, again, when he talked to you about the many body physics. Many body physics, in this case, the bodies are the stars. And the stars in a galaxy, you can think of that they doesn't talk to each other, they doesn't collide. So they are kind of collisionless mass distributions in the galaxy. And I can consider the stars as single particles. What's happening inside the star is completely of no importance when you talk about the galactic structure and dynamics. Now, let me ask you to do a home exercise. You can look up any book or even internet for finding out the numbers, but this is what you have to figure out. The three time scales. One is how long a star lives. One is how much does a star take to go around the galaxy. You have learned about the rotation curves and the stars are going around. So how long does it for a star to take a full round? So the immediate question you can then ask is, will a star live long enough such that it can make a full round in the galaxy? And then the other question is that how long does a galaxy live? So what is the lifetime of a galaxy? So you can ask the question, even if the star lives long enough, will it make many rounds around the galaxy before the galaxy disappears or it changes to something else? It turns out that all these questions will essentially let us understand if the galaxy in its lifetime has a steady state, meaning that something in the galaxy doesn't change much during its lifetime. And it turns out that is the case, that the galaxy on the average does look the same for a long part of its lifetime. So you can ask the question now. We are talking only about the stars in the galaxy for this lecture. And we can ask the question now, what we can use to quantify this distribution of position and velocity of the stars. And we already know such a thing, which we call the distribution function, which gives me the number density of particles, in this case stars, at a given point and around that point, with a given velocity and at around that velocity at a given time. So it's usually written by F. And you have learned in your many body physics part of the course that the collisionless Boltzmann equation is the equation which governs the evolution of the distribution function. And as you have said, that for a long part in the galaxy's career, the galaxy's lifetime, the galaxy doesn't change its properties much, essentially means that the distribution function should not depend on time explicitly. And in that case, the del F del T part of the collisionless Boltzmann equation can be thrown out, that is 0. So I get this. Why I am using collisionless Boltzmann equation here? Just because, as we said, that the stars are far away and they don't collide with each other. So we can easily say that collisionless Boltzmann equation is the equation that is to be used. Now each star, though they doesn't collide with the other stars, there are say 10 to the 11 stars in a galaxy. Each of them fills the potential of all the other 10 to the 11 stars. So all the 10 to the 11 stars in a galaxy kind of creates a mean field potential, which I will call phi. And each individual stars sees that potential. So if it sees that potential, I can calculate the acceleration of the star. That's straightforward, because minus grad of phi gives me the acceleration. And then I put that back in this formula, and then I get this equation, which is giving me what is the steady state distribution function supposed to be, given that potential. Here I have two gradient operators, gradient over x and gradient over v. Gradient operators, we already know that, so say gradient of x in Cartesian coordinate is essentially del del x cap plus del del y cap plus del del z cap. Similarly, gradient of v is nothing but del del v x cap, etc. So this can operate on f because f is a function of the v vector, that's the vx, vy, and vz components of the vector. So this is the equation. Given the potential, will tell me what is the steady state distribution function. And that steady state distribution function has the information about the steady state behavior of the galaxy. Nice. So first step is then to know what is the steady state distribution function. And it depends clearly on the gravitational potential provided by all the stars. But remember that once you know this potential, it depends on the position of the stars. And the steady state distribution function is essentially telling you where the stars are and what is their velocity at a given time. At the next time step, all these will change, but you still expect that the potential and the steady state distribution function to remain the same. So how to go about this problem? Well, you do a trial and error approach. So what you do is the following. You first assume, you take a good guess on the potential, calculate the steady state distribution function. If you have a computer which is good enough, it has to be a very, very strong computer. I don't think such computers exist today, but say 10,000 years from today, what you do next is, given the steady state distribution function, you calculate the density and evolve the stars in the galaxies in their orbits. Calculate the stellar orbits, find out where the stars will be in the next time instant. Modern day, you cannot do that. As we said, we don't have so difficult, so powerful computers. So what we do is we take the moments of the collisionless Boltzmann equation. It gives us essentially the fluid equations. The first two moments are the continuity equation and the Euler equation in this case, and we use these to see how collectively the star moves to the next time step. And once that is done, we again recalculate the distribution function. And this distribution function should follow the collisionless Boltzmann equation in steady state. If it does, that means that the potential that we guessed was right. If it does not, the potential that we guessed was wrong. So we change the potential a little bit and do the process again. And once we do this, after several iterations, we get good approximation to the potential in which the stars are moving. Once you know the potential, then I can again solve the steady state collisionless Boltzmann equation. Now for the actual potential of the galaxy, I get the different moments of the CBE, the collisionless Boltzmann equation, and from there I can calculate several things of the galaxy. For example, when you calculated the rotation curve, you essentially use the first moment of the collisionless Boltzmann equation, and that gives you the rotation curve of the galaxy. You may not have understood that at that time, but it's essentially what you are doing. So that's the first part of the lecture. So that gives you an overview of how you actually approach to the problem of galactic structure and dynamics. Once you know that distribution function, that has all the information about the galactic structure and dynamics that comes from that potential. And I have already told you how to fix those. In practice, it's a very, very difficult job. The type of structures you are dealing with is difficult. The type of potentials you are dealing with is difficult. But more or less, people know how to do it. The next part of the lecture, what we'll do is to look at the orbit of individual stars. Why it is important? Because it's, as we said, that it's not possible to study all the 10 to the 11 stars in a galaxy. But sometimes we do study them. May not be in a galaxy, but maybe in a globular cluster. Or sometimes you follow the orbit of the stars to stress something else. For example, the orbit of the stars were traced near to the center of our galaxy, and from their orbits, we concluded that there is a black hole at the center of our galaxy. I'll not go into the details, any details of this. This is 40 years of work, and If you are interested, you should look at it. Okay, so let us start what we are going to do next. We are going to look at the orbits of stars in spherically symmetric potential. When I say spherically symmetric, I mean if I use a spherical polar coordinate centered at the center of the galaxy, the potential or the force only depends on the r coordinate. It doesn't depend on theta or phi coordinate. But it doesn't mean that it has to be a minus 1 by r potential. A minus 1 by r potential comes only when you have a point-like mass distribution in gravity. As you may imagine, the stars are distributed over the entire disk in a disk galaxy, or in this ellipsoidal structure in an elliptical galaxy. So for any star in the galaxy, inside the galaxy, obviously it will not see a 1 by r potential. It will see a more complicated one. But whatever it is, we are assuming for the time being, it depends only on r. So in this case, the force per unit mass, and we'll consider all the dynamical quantities per unit mass here. This is the per unit mass of the star of which we are considering the orbit. And it's given this way, so it will depend a function which is a function of the r coordinate only, and then the radial unit vector. Obviously, the potential also will depend on a different function of r coordinate. Now, what does our high school physics knowledge tells us about such a force? It tells us that this is a conservative force, which means that the energy is conserved. It also tells us that such forces, which are the central forces, the angular momentum and the z component of the angular momentum is also conserved. The conservation of the z component of the angular momentum gives us the fact that these orbits lies in a plane, and the conservation of the angular momentum we can use in our dynamical analysis. Now, because the orbits lies in a plane and we are talking about a spherically symmetric type of situation, we can choose the polar coordinate where r and phi are the coordinates which will which will give us the trajectory of the particle. So the total energy for this system can be written in terms of the kinetic energy and the potential energy. Well, we are writing the energy per unit mass, so it's kinetic energy per unit mass plus the potential function, which is the potential energy per unit mass essentially. And the kinetic energy will have a component from the r coordinate and it will have a component from the angular coordinate phi. So the r coordinate component is half mr dot square, so m per unit mass, so it just gives you half r dot square. The angular coordinate contribution of the kinetic energy is half r square phi dot square, which is as usual. And we also know how we can write down the angular momentum. The angular momentum per unit mass, if I call it small l, it's r square phi dot. This is again is a very straightforward thing from your plus 2 physics, so I'll not go into the detail of it. You can just figure it out. And if I put that back over there, I can eliminate phi dot and I can write everything in terms of the r coordinate. So here I have the energy per unit mass half r dot square plus half l square by r square plus phi r. Everything depends on r and its derivative. So I can write dr dt whole square, which is this r dot square over here in terms of everything else. E and L are the constants of motion here. And I guess I get dr and dt relation this way. Remember that E and L can be different for different stars. Obviously, they will be different for different stars. But for a given star that is moves along the orbit, they doesn't change. Fine. So we'll come back to this expression again, but before that, let us look at the energy equation once more. As we have already said, that it has only r coordinate, it doesn't have phi coordinate at all. So it looks like is a kinetic energy per unit mass for the r coordinate, and then there is this whole bunch of thing which depends on r, which I can call an effective potential. So then this energy equation just looks like the energy equation for effective potential, which is this plus that. And this is a very good way of analyzing the system, and it will be very clear as we go through these and the next two slides. So what I do here is first identify the fact that the energy per unit mass, the effective potential or potential function, phi and L square by 2R square, all of them has the same dimension. So all of them I can plot in the y-axis, a level which I am plotting obviously, and the x-axis I plot R. There is an unfortunate thing which has happened in my choice of notation here. Let me apologize for that. I have chosen phi for both the potential here and the angular coordinate. But I think that it is very clear to you that this is the angular coordinate that you're talking about, and this is the potential, gravitational potential. Anyway, so let us plot several things. So first start with L square by 2R square. So L square by 2R square as a function of R is just a 1 by R square plot, scaled by the value of L square. That's this dashed line over here. It starts with infinity at R equals to 0 and then goes to 0 at R very large. Phi R is an attractive potential, and the attractive potentials we know are usually negative. So I plot, I choose a count completely off and phi R, and I plot it this way. It can have many other different shapes, but let us just choose it this way. So it's a dashed lines, which is again infinity at R equals to 0. That's my choice, but it has to be 0 at R very large. That's a choice that you have to have for a gravitational potential. Now the phi effective is just the addition of these two, and I have tried to draw the addition with this solid line, which is what we will discuss from now on. And again, remember that this solid line will completely look different if for different choices of phi r and the value of L. It may look like it starts from minus infinity, go up, go down, and then go like that. It may start from minus infinity here and then go up and go like that. It can have several different types of forms, but let us concentrate with this because that will take us home on the points that I'm trying to mention here. Let's start with an energy which is E equals to E1. Remember that to draw this curve, I have already used up one of the constants of motion, which is the angular momentum. So let us use the energy now as the constant of motion, and the energy I choose to be here. Energy can have any value, so I've chosen a positive value here. As I said, that different stars will have different energies. This is a star, you assume it has a positive energy. And I consider 2 points here. One is here and this here. So for this point, this is the value of the energy, and the effective potential is well high up here. So if you look at this equation, this value of the energy is less than the effective potential value, which means this term has to be negative. But well, that's not possible because I have a r dot square sitting over there. So r dot square less than 0 is impractical, which essentially means that the particle cannot reach here. Essentially, this line acts as a barrier for the particle, which the particle cannot penetrate. So it's called the centrifugal barrier. So the particle which has an energy positive, it can go to infinity and then comes from infinity, hit the potential, the centrifugal barrier, and then it can go back to infinity. So the particle can go back to infinity. So this type of orbits are called unbound orbits. Let us not talk about the energy equals to 0. This I leave to you. Let us talk about a star which has energy equals E3. It's negative, just below 0, say. And here I show you E equals to E3 again. And I consider this position first. And here exactly the same thing happens, which happened at position A. Here the kinetic energy will come out to be negative, which is not possible. Again, if I come here, the kinetic energy will come out to be negative, which is not possible, which essentially means that for this stars, it can either go at a radius value which is less than R1, which is the radius here, or it can go at a radius value which is greater than r2, which is the radius here. So it has to be bound in between these two radius. If I draw the potential, if I draw the surface of the disk, so this is the r1 radius circle, this is the r2 radius circle, the star has to be always there somewhere inside. It has a very boring life, like the quarantine life we are leading now. So these orbits are called the bound orbits. As you as your energy goes close to zero, the R1 and R2 separates out. As you can see, if I draw this energy line here, it will be R1, R2 minus R1 will be larger. As we go down in the energy, these two lines, these 2 points come together. R1 and R2 comes together. So this comes this way and this comes that way, unless it hits R0, where these two merges. And at that point, the particle or the star can have only one radius orbit. So that is the circular orbit for the star. It's a very special orbit. And the epicyclic approximations that you are looking at earlier in the course are the orbits which are near to that, r equals to is RC. So you have learned about, so these are called bound orbits. So you learned about open orbits, unbound orbits and bound orbits. And let us look at this expression again. So this expression tells you how much is the change in time given certain change in r. So let us ask the question, for a star in the bound orbit, how much time does it take for it to go from R1 to touch R2 and then come back to R1 again? And that we can figure out just integrating this expression from R1 to R2 twice. So R1 to R2 and R2 to R1, both the same, so just twice. And that we call TR. So TR is the time period, the radial time period for the stars, radial because the radial coordinate comes back to the same position after this time. But you can ask the question, in this unit of radial time, how much angular distance phi? This phi is the angular coordinate phi, not the potential phi, does the star has traveled? It is very straightforward to do because I know that L, which is the angular momentum per unit mass, is given by r squared d phi by dt. So I can figure out how much is d phi in terms of dt. And then I had this expression for dt in terms of dr, which I can substitute. So I get d phi equals L dr by r square root over of 2 e minus phi minus L square by r square. And then I can integrate this just like r1 to r2 twice to figure out how much angular distance does the star have traveled as it has moved from R1 to R2. So it has started from R1, it has gone to R2 and then come back to R1. What is this angular distance it has traveled? So let me show you using a notation. It will be easier for you to understand, I guess. So the star starts from here, goes there, say, and then come back here. This is the angular distance that it has traveled. So that is delta phi. Okay. And I don't have no idea. Okay. So once I know that delta phi, then I can ask the question that how much is the delta phi for the star to go around in the orbit completely once? And that's obviously 2 pi, right? The phi coordinate changes by 2 pi as the stars go around all the phis. So now I have this following informations that the star takes clear amount of time to go around delta phi amount. So how much time will it take to go around 2 pi? And that we call T phi. So T phi is the azimuthal time period, which tells you how much time does a star take to go around in phi coordinate. And this gives this expression where you see that this 2 pi by delta phi is no reason it has to be an integer. Even delta phi is this very complicated expression, and depending on the phi r and the value of L square, it can be anything. If it is an integer though, what will happen is like this orbit, where the star starts from here, it goes around, it makes a very complicated orbit, but after a certain time, it comes back to the same r and phi. And that's important, that it comes back to the same r and phi. If it does, that will only be the case when delta 2 pi by delta phi is an integer. The star will always remain on this thin line. So it will always follow this part of the orbit. It will never be able to go anywhere else in the disk. So these are called closed orbits. On the other hand, if it is not an integer, just like what I have tried to show here, so the star starts from here and it can have an orbit like this. You may think that I have just mocked it up. My drawing is bad, but still it can have an orbit like this. And it just misses. It doesn't come back here. If it would have come back here, it would have followed a closed orbit again. But here it doesn't come back. It goes like this. So that is called an open orbit. Most of the orbits in a star are open orbits. It turns out that there are only two types of potential which gives you closed orbits. One is the harmonic oscillator potential, and the other is the -1 Bayer potential. All the other potential gives you open orbits. Okay, so that's all that I had to tell you about the stellar orbits, and that all I had to tell you today. We have learned about the stellar orbits. We have learned that there are orbits which are bound, there are orbits which are unbound. Now, most of the orbits in a galaxy are bound. That's why the star stays in the galaxy. It doesn't fly off from the galaxy. Because most of the galaxy orbits in a galaxy are also open orbits. So they doesn't close. And that has a very interesting consequence. Remember that near to the r equals to r0, the bottom of the potential, we said that we have those epicyclic orbits. And those epicyclic orbits have the nice thing that they go around in kind of ellipses, but it doesn't quite always make a full ellipse. So they are still open, which means that the ellipse may like starts from here. When it comes back, it slightly misses the original spot. So the ellipse kind of rotates. Okay. So that is the almost elliptical but open orbits. It turns out that all the planets in the solar system does the same thing, because the potential is not exactly 1 by r. There are extra terms which comes because of the general relativity. But anyway, this rotation of the ellipse has to do with the spiral structure of the galaxy, which we will touch upon in the next lecture. So thank you. If you have come up to this, I'll request you to post all your doubts in the classroom comments in the Google Classroom, and I'll see you in a couple of days again. Thank you.